So nuclear energy is extremely important because it promises a bright new future. There are two kinds of nuclear energy, nuclear fission and nuclear fusion. Nuclear fission is where you break things apart and it releases a lot of energy. Nuclear fusion is where you force things together and equally it creates a lot of energy. Now what you're forcing together is the nucleus, the centre of an atom. So you want to strip away the electrons and you want the centres of the atoms, and when you push them together, of course those centres are both positively charged. They want to push apart again. You need to overcome that initial long range push apart so they get close enough together so that the nuclear interaction will pull them together and the strong nuclear force will make them smash into each other. Now what we use a lot, or what is used a lot, is hydrogen. Hydrogen is one proton, and a more favoured one is deuterium, or heavy hydrogen, which is one proton and one neutron. You can also use tritium, proton and two neutrons, but they are the favoured materials because they're the lightest and the most abundant, and we can get those to smash together. If we can get them to smash together, we will get nuclear fusion and we get net energy out. Now, in order to do that, of course, you've got to do several things. First thing is you've got to strip the electrons away. The next thing is you've got to get them really hot so they're moving quickly. And the third thing is you've got to bring them close together. You've got to bring them near to each other because fusion is a probabilistic event. These things are always zipping around. At some level or other, they are going to hit each other. Just that normally they hit each other so rarely, it's of no use whatsoever. So we need to up that rate at which they hit each other. And you do that by bringing them close together. Now there are three kinds of nuclear fusion. There's hot fusion, which you see in things like the sun. There's cold fusion, and I don't mean the Pons and Fleischmann. And then there's pure confusion, which seems to surround this entire subject. With hot fusion, what we're trying to do is mimic the processes that go on in the sun. And we do that by creating, one way, a large magnetic field, and that's in a device called the tokamak. It creates a large magnetic field. You heat up your hydrogen ions to super hot temperatures, confine them close together, and we get fusion. Another way of doing that is with inertial electrostatic confinement. So instead of using a magnetic field, we use an electrostatic field which creates a potential, well, holds that hot plasma in a confined space, and we will get fusion. Of course, the third way is the way the sun does it, which is gravitational. Now, on the cold fusion side of things, and there are several variants that are really looking exciting and are real variants. There's something called lattice entrained confinement. There's some metals will absorb hydrogen. When they absorb hydrogen, they bring everything close together in the metal lattice, much closer than they would be if they were zipping around. Then all you have to do is hit them with a bit of energy and they will fuse together. And it was in 2020 when NASA did exactly that. The other way of doing this is called pyroelectric fusion. There are some materials, lanthanum titanium oxide for instance, where if you heat them, they create incredibly strong electrical fields, and those fields are strong enough to hold the hydrogen in close proximity. The next one is what's called muon catalyzed fusion. As I said before, there's an electron around the atom, and that keeps the atoms apart. A muon is a negative electron with only one difference. It's much, much heavier. It's about 197 times heavier. So the hydrogen atom with the muon is very much smaller, and because it's so much smaller, you can actually bring them much, much closer together and increase the probability of fusion dramatically. So muon catalyzed fusion is another one of those real cold fusion, room temperature fusion processes that's receiving a lot of research and actually doing really well. So far, the issue with those fusion processes is the net energy. You have to put more energy in there than you can get back out. So the muon, for instance, it takes about twice the amount of energy to create a muon than you will get back out of it. The final area that we mentioned was the confusion, this collection of ideas that have been suggested. So there are two main reasons for this arising. One is the kindest explanation, and it's called pathological science. Pathological science is where a scientist is doing something and he wants something so much to happen and to be true, and he wants to believe what's happening that he ignores the evidence and he makes a mistake. And when he makes that mistake, he isn't going to back down. He invests in the mistake, and unfortunately it gets worse and worse and worse until they're completely discredited. And this is exactly what happened with the original cold fusion experiment and Pons and Fleischmann. And it's also why this stuff is all now called low energy nuclear reactions. So there's an attempt to distance itself as much as possible from the original debacle that surrounded Pons and Fleischmann. And I would say that was the kindest explanation of why some of this stuff arises, and you can put an awful lot into that if you want. And the second part is why I chose confusion. See what I did there? Play on words. Fraud. There's an awful lot of money involved in this, both in research grants to the tunes of tens of millions of dollars, to false companies conning investors, again to the tune of tens to not, if not hundreds of millions of dollars, where you will rush to set up a company with this idea and then get investment, and of course it never comes to anything. So those two main reasons why this confusion arises. And I think a fair example again of pathological science would be the thing bubble fusion. Bubble fusion was a cavitation fusion. It was noticed that if you had a big bubble and let it cavitate, then there were anomalous heat results from it, and that was thought to be fusion, and it went for quite a long time until it was gradually disproved over something like 10 years. Now, a lot of the people who are practicing fraud can be very litigious, and Blacklight Power is one of those people known for being litigators. So there's a physicist called Park of Park and Nobel fame, who are heavily involved in inertial electrostatic confinement, that criticised Blacklight Power till he got a letter from their lawyers saying they would sue him if he didn't stop doing it. Now, I'm not saying anything about Blacklight Power. Maybe it is one of those areas of pathological science, but maybe it isn't. Another infamous one is the Patterson cell. The Patterson cell was just a collection of materials in a tube that mysteriously did something. And I suspect the other famous one is the ECAT, the Rossi device. The ECAT was actually tested independently, but it was never unplugged, and none of the materials were allowed off site for analysis. It was just shown, there you go, it's working. Isn't that awesome? And the main reason, as I say, you get these kind of things is, honestly, it's to do with the money, which is unfortunate. Cold fusion is a real thing. It actually works as per NASA, and there's an awful lot of research going down there because it just would be so much cheaper to do it. Problems to overcome, and that research continues. And of course, like all of these things, when it's attracts so much interest, then scams and misguided efforts are also continuing. Which is exactly the case in batteries, of course. So this thing happens all over the place at all the time, but cold fusion is certainly real, alive, and offers great promise. Anyway, I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.